record. You get binding. You can have S2. This one's called a sequential reaction. So this right here would be the ternary complex, or three things bound. Okay, that does not happen in the ping-pong. Okay, and then this would go on and on to make, either one product or two products, depending upon, the synthesis or if it's an exchange reaction of some sort. That's one. That's called a sequential, or chronological addition. Then there's another one that's called random, which is E plus either S1 or S2. Oh, I probably should use a different color. Here, let me switch colors. That way it's a little easier to see. And you get ES1 plus S2. Or you can get ES2 plus S1, to where it doesn't really matter the order which they bind. Whoops, my arrows got a little crazy. And then I'm going to draw it this way because this way it's a little easier to understand. Maybe there's two separate binding sites. It means the same thing as what I did before. Once again, this is a ternary complex. It's just a different way of drawing it. And then this would go on to make either one product or two products, depending upon what kind of reaction is occurring. Okay, but that's not what's happening in ping pong either. So neither one of those is what's a ping pong reaction. There's no ping to the pong or the pong to the ping or anything like that. So, all right. Technically, in the ping pong reaction, you don't get that ternary complex. So what happens is first a substrate binds. Usually, what happens is it covalently modifies the enzyme transiently, meaning only for a short period of time. Then the first product will leave. Then the next substrate comes in, and whatever was covalently added to the enzyme gets added to the second substrate, and so therefore this second product will leave. And so I'll try to draw it. I don't usually draw the ping pongs as well. So what I'm saying is, let me change the colors once again so that way it's easier to tell. So we have E plus the first substrate. Typically, it's binding this one. And I'm going to clearly show it as, and that's a prime, meaning the enzyme itself was changed somehow. Product 1. So then we get the E prime. Of course, product 1 leaves. Plus S2, it has to bind. So now we have E prime S2, E P2, and then, whoops, I ran out of room, but then the second product leaves, and you get your original enzyme back. And so that's why there's usually a lot of steps. Aminotransferases, which are also called transaminases, which sounds like a car, a car enthusiast dream. Probably the textbook, quote-unquote textbook example that you often see for this ping-pong mechanism. And ping-pong. Or this double displacement kind of mechanism. Because what would happen, so for example, if you're trying to do the first substrate would already have an amino group on it. Which one is an amino group? Since not everyone has had organic chemistry, I don't think. I know. What is an amino group for aminotransferases? I gave it to you guys in that cheat sheet in the very beginning of the semester, since not everyone who has, you usually have to memorize them in organic chemistry, and you definitely have to memorize them in biochemistry. What's an amino group look like? What does it have? An N? And then it's an N that is bound to at least three things, okay? So sometimes it's shown like this way as NH2, but what's different about it versus a carbon-based one is, or maybe an NR2 or even an NR3, because an amino group can be positively charged. But that R means it could be anything, okay? This would be the simplest of the amino groups, NH2. But once again, it could be two different carbon groups hanging out. It just can't be an oxygen or maybe a phosphate or something like that, because then it's no longer a traditional amino group. Okay, so what happens with the ping-pong mechanism is first you'd have, so one example with aminotransferase, this is it? Yes, okay. You'd have your enzyme, and whatever's going to be the amino donor would bind, and it puts its amino group onto the enzyme. That's why that'd be the prime there in this example. So now it's called the keto acid then. The keto acid would leave. The group that's going to be getting the amino group comes in, binds to the enzyme that already has an amino group, and then the enzyme gives the amino group to that group. So now it has the amino group, and then it leaves, and you have the original enzyme back. Or that's one way to do it. Another way is the fact that instead of the amino group being transferred to the enzyme, it's everything but the amino group that gets transferred to the enzyme, because the enzyme itself may have the amino group. So let me show you what I mean by that. That's where this comes into handy. So aminotransferases actually do 3 different jobs. The first one, I actually don't like this figure that well, because unless you're really, really familiar with the electron pushing and how these work, it is tricky. Okay? But what happens is the original enzyme, what they're not showing, it uses it's called a cofactor. This is pyridoxal phosphate. It makes what's called an aldamine, okay, which is really confusing if you don't know what that is, but it's what was an aldehyde and an imine, so that's an imine group. But this is the amino group that's coming in. But the enzyme itself originally had a lysine, okay, and the lysine is has a nitrogen on the end of it, and it binds to what was the pyridoxal phosphate, okay, and it's actually the pyridoxal phosphate that does the chemistry portion of it, and not the enzyme directly itself. So the enzyme just is holding it all into place. So this is the amino donor, and what we can see is, then you can follow it on through, and you get the first product, which is the alpha keto acid, and it's got the nitrogen that's added to, technically it's not the enzyme directly, it's the cofactor that's bound to the enzyme, and then you get the reverse. Okay, and that's how you get the second amino group. That's why I don't like this one. But that's one type of reaction. So aminotransferases do 3 things. The most obvious is the fact that it does an aminotransferase, so amino transfer groups, or transfer reactions, it should say. Okay. The second thing is that it can do a racemization reaction, which we'll talk about what that is in a moment. And then finally, they can also many times do decarboxylations. Okay, everybody know to get caught up. When we say racemization, what does that mean? What is that associated with? What is a racemic mixture? Do you remember? Pardon? R and S, and in biochemistry kind of stuff you talk about D and L, but it's the same principle. But yeah, so it's a mixture of stereoisomers. Okay? Whether you're using D and L nomenclature, plus and minus from organic chemistry, or R and S. R and S comes from the con prelog in gold, I think. I don't remember the names now. Okay, but I know con is one of them, one of them is prelog. I can't remember if it's in gold or gold is the third name. But it's R and S. Plus and minus and D and L are the easier ones to remember for me. And so, but it has to do with stereoisomers or enantiomerization. You can think of it as racemization, you can say enantiomers. I'd rather do that, or it's a type of isomerization. What are enantiomers? Have you guys covered anything like that in Gen Chem yet?
We haven't, but aren't they like mirrors of each other?
They are, kind of. So, yes, that's what it's related. You know, in theory, you know, your hands should be enantiomers. They're not going to be perfect, very rarely are they perfect. You know, because usually you have one hand that's far bigger than the other. But the idea is they are isomers of each other where the mirror images are not superimposable. So that's why, I used to always say, unless your parents were like, you know, related to each other, your thumb and your pinky shouldn't line up. I said that one time and I had a student that was really freaked out because she went like this. She's like, you know what's wrong? But she did. She was like really freaking out. Like, no, remember this is the mirror image, and so what happens is when they flat, they don't line up. Okay? But you don't have to worry about that. But so what happens though is in vivo, you know, in organic chemistry, one of the rules of thumb is that if you take, and it's called a racemic mixture if you have a mixture of, like, I'm going to call them left hands and right hands. Okay? If you have a mixture that's just mixed up together, it's called a racemic mixture or racemization. And if you take something that's a racemic mixture and you modify it, you're going to end up with a racemic mixture in organic chemistry in vitro, unless somehow you can modify the environment it's in to be. In other words, the use is called chirality. If it's achiral, there's not a stereocenter there. If it's chiral, there is. So unless you can somehow modify it in vitro for a chiral environment. Now our body already handles that pretty much already, because almost all enzymes are enantiospecific. They're going to be specific for, you know, the left hand or the right hand. Because that's the way that the binding sites operate. So you can imagine amino acids by their very nature are either going to be they call D and L in biology, biochemistry. It stands for dextro rotary and levo rotary. Dextro means right, levo means left. And literally, you put it in the polarimeter. If it rotates it to the right, it's dextra rotary. If it rotates to the left, it's levo rotary. That's why it's pretty easy. RNS doesn't work that way. It makes it more difficult. And plus and minus does too. If it rotates it in a positive direction, it's a plus. If it rotates it in a minus direction, it's a negative. And so that's why D, L, plus and minus are a little easier to use than RNS. But what I was going to say is you can imagine only certain amino acids, there's the only amino acid in your, does anyone from biochemistry remember what's the only amino acid in protein that it doesn't matter, it can't be D or L? Glycine. Okay, glycine is the only one that's achiral in itself. It's completely achiral. It's because it's got two hydrogens. A little cheat way for those of you who haven't had organic chemistry yet, I don't know if you learned this way, is carbon has to have 4 bonds, okay, in order for it to be even considered chiral or achiral. If there are 4 different things, it's going to be chiral. It will be there will be different enantiomers. At least 2, if not more. Okay, now if it's a cyclical group, you actually have to go around the circle to see if they differ, so it becomes a little more tricky. Like proline is that way in amino acids. But that's just the easy way to do it. If a carbon doesn't have 4 different things on it, it's not chiral. If it has a double bond where it could only be 3 different things on it, they call that prochirality. And a lot of times in organic chemistry, they just ignore it. Well, I should say, at least organic chemistry 1 and 2 would ignore it. If you went to higher level organic chemistries and medicines and stuff like that, and medicinal chemistry, they wouldn't. They would talk about it because our body also can distinguish at times different prochirality. Okay? But that's just a little here and there. That's only with respect to carbon. You can imagine nitrogen do something similar with the 3 bonding. Phosphates can do up to 5 bonding, you know, things like that. But we're going to stick to carbon. And so the important thing here is the amino acids. That's the building block of proteins, in case you've forgotten. And there's, with the exception of glycine, all of the other amino acids have to be a very specific enantiomer. Okay? You can get the other enantiomer, but you have to have a way to modify it, to turn it to the correct one, to the D. Okay, if you start with an L, you're going to turn it to the D. All right, so in this, and aminotransferases do that. That's one. So that's what racemization. It's probably the most difficult one to explain. Aminotransfer is easy. The amino group gets tossed back and forth. Racemization, you can change a D to an L amino acid or an L amino acid to a D. R to S, S to R, plus to minus, minus, plus. Decarboxylation literally means you lose a carboxyl group and it's going to be, we're talking about carbon dioxide. So in vivo, anytime you do decarboxylation, it's going to be carbon dioxide. Now, if it's carboxytransferase, that means it's moving it. It doesn't necessarily mean that you're getting it off in the form of carbon dioxide. Okay. Which, sometimes I forget to specifically point this out in biochemistry, so I know I haven't pointed out there. Reason why, does anyone know why do we exhale carbon dioxide? What does it imply? What does it mean? Like, why do we get rid of carbon dioxide?
Because it's not good for us to keep in our body.
Anyway, what is it indicative of? What have we done to this poor carbon? You will use it, but we have used it for all its worth. This is one time I'm using something. We have used it. We've got all of the chemical potential energy out of it in the form of electron transport for the electron transport chain. It's no good to test anymore. We're going to kick it out. So it's good. So it's been completely oxidized. This is as oxidized as a carbon can get. It's the highest oxidation state. And so we literally, if you take your saturated fat, which is what the biochemistry is saying right now, take your saturated fat, that's when it's fully reduced, except for the one carboxylic end. And so that's when it has the most energy. So your saturated fats, there's lots of potential energy in there, and then with each what's the word? Cycle of the beta oxidation, we get rid of it. Well, we don't get rid of carbon dioxide. We get rid of it in the form of acetyl-CoA. Acetyl-CoA eventually becomes carbon dioxide. But we completely use all of the energy from it. Okay. It's just that, especially in Western diets, it's much higher than saturated fat than what our energetic needs, metabolic needs are needed. So these are the three basic types of reactions that the aminotransferase uses. Okay. Now, since some of you haven't had organic chemistry yet, I will take a little bit slower to explain what this means. Let me make it a little bit smaller. Actually, I'm going to make it a lot smaller because, like I said, I don't really care for I don't think that this will. Let me see. So that's what we're seeing right here. Okay, so we've just kind of taken all that away. And so the way to do this, and one thing that they don't show you, because by the time biochemistry rolls around, they just assume that you know, is how it got there in the first place. Which this lysine, this was a nitrogen, which was an amine. So it looks like this. That's the long arm of it. It's a hydrogen, low and pair electrons. And one rule of thumb, I don't know how Dr. Salvatore teaches it, but one rule of thumb is we always, how they say, show me the money kind of thing from Jerry Maguire, which really is older than you guys. But what I was going to say is you always follow the electrons. It's the electrons that do the chemistry. Okay, so that's why we always look for things that are nucleophiles. They attack things that are electrophilic. They're electrophiles. Nucleophiles means it loves the nucleus. Electrophiles love the electrons that are coming to attack its nucleus. And so that's why a nucleophile, by definition, has to have one pair of electrons. And this nitrogen on the lysine does, the lysine of the enzyme, I just drew. And so what it does is it goes and it attacks what would be the carbon of the carbonyl group of the pyridoxal phosphate. And it does so twice. It attacks it once, this bond will pop off to make lone pair electrons in it. And then it'll attack it a second time, and the second bond will pop off. And so this oxygen leaves in the form of water. So that's how it got here in the first place. So that's why we end up with what looks like the imine. Imine is a carbon and nitrogen. That's a double bond. It's called an aldamine because originally it was started. The imine was formed from an aldehyde. Okay. So now we're going to see what happens here. I shouldn't say, because I'm guilty of it too. Because people just get used to it. They show it being protonated. So there's the extra proton. So that nitrogen's got a positive charge on it that once it gets inside the environment of the enzyme, that extra hydrogen can come off really easily. Okay. So whenever that happens, it can act like a nucleophile. So what they mean scientifically, they may even use words like perturbed pKa. That's just a fancy way of saying that the hydrogen that normally is on there can come off really easily. And so I wanted to point that out because then it doesn't really look like the NH3, it looks like the NH2, or at least behaves like an NH2 with the lone pair electrons. And so all this does is this nitrogen comes in and displaces, it reacts it twice, it displaces the lysine of the enzyme. It's still held in the enzyme, but the enzyme is no longer attached to the pyridoxal phosphate. Instead, now the imine is between the, what's going to be the amino donor for the aminotransferase, okay, and the cofactor. Okay, so let me take that one off so you can see it a little bit better. Where's undo? I tell you, they completely changed it. Okay, so this is what it looks like now. The amino acid donor, I should say amino acid donor, the amino donor, I'm sorry, is now covalently attached in the enzyme binding site. So that's where we had that E prime. So this would have been the E plus the S1, and now we have that ES1 or that E prime S1 complex. Okay, so it's covalently attached. The B just stands for, does anyone know what is the B? It's not boron, okay, but we use B's a lot in biochemistry and biological phenomena. What is it? It's just base. In fact, we use the term general base, okay, because it just means it's your generic base. Anything that has those lone pair electrons that can do the attacking. So some of the amino acids that are important for stuff like that could be like aspartate or glutamate, because they have carboxylate groups on it. It could be another lysine. It could be histidine. Histidines are really good. You know, there are lots of amino acids that would be able to fall in place of that. Or a water can. Sometimes in vivo, water is really important for doing that because water's got lone pair electrons. So water can take a hydrogen, become H3O plus temporarily, give up a hydrogen, can become an OH minus temporarily, things like that. So we call them general acids or general bases, and that's just a general base. Okay, so this general base here with its lone pair electrons just comes and swipes that hydrogen, but it's only swiping the nucleus part. Remember, hydrogen only has one proton and one electron. The electron, what that's showing you is those little, what is that blue? The blue arrows shows you the movement of the electrons. Okay, and if it's got, it's kind of hard to see, but if it's got two barbs, like the two pointy parts on the arrow, versus the way that we do, so I mean, here, let me do it. Most of the time, actually, I don't want to misspeak. If it looks like this, that means both electrons are moving. If it only has a single barb, it means only one electron is moving. Okay. All right. So what that means is this generic base here comes and takes the proton. The electrons from that hydrogen, there's just two that had been holding that hydrogen onto the red carbon, they stay behind. Which should make sense. Carbon's a little bit more electronegative than hydrogen. Mm-hmm. So this is where, if you had me for organic chemistry, I would always say sound effects optional, because they come, and that's how I learned it too. And so come in, boom, something has to break or give. And so what breaks? So the hydrogen cannot make two bonds. Hydrogen can only make one bond. So it's the two electrons that had been holding it to that carbon actually will break away from the hydrogen's proton. So now what's not shown is that hydrogen, I really wish it wouldn't do this every single time, will look like this. It's actually covalently attached to that B. Whoops, I should have put that right there. It's over here. Okay. But then this comes down, boom. Something has to break or give once again, because otherwise this nitrogen has too many electrons. Nitrogens cannot violate the octet rule. And it would have 4 electrons there, 4 here, and then the 2 from that hydrogen. So something has to break or give, and that's what this arrow is showing. 2 of those electrons go down here, boom. Sound effects optional. To make a double bond between the 2 carbons, something again has to break or give, or this carbon's going to have extra electrons. And so what had been a double bond for it comes down to form a new double bond Boom, sound effects optional. And then something's got to break or give, and lo and behold, it's these two electrons that had been in that double bond go boom into sound effects optional to the nitrogen, which now the nitrogen is perfectly happy. This one, that's why pyridoxal phosphates are really powerful tools. In the sense that sometimes they're called electron sinks, because see, it's like the electrons going down the drain, sinking down to the bottom, that kind of thing. And because it had started off being positively charged, now it's neutral. And so all the electrons down there. And then you can reverse it as well, which we do in just a moment. All right, so the whole purpose of that is we still just have what would be the amino donor. It's still now covalently attached to the enzyme complex. We haven't actually made our first product yet. And so what we do now is we do the reversal of that. Okay. And the reversal is those electrons go up here to reform the double bond. Boom, sound effects optional. Reform that double bond. And then this double bond, instead of reforming here, which in theory it can, but another option is it actually comes back and notice they're showing it just as an H+. That would be a generic acid. But if you notice, we have already lost an H. So it could be this hydrogen. It doesn't have to be. They don't show that. In organic chemistry, I don't know about Dr. Salvatore, but a lot of times the books are really particular. They want you to show exactly where's this hydrogen, where's that hydrogen. In vivo, we can't do that because our bodies are water-based, and so waters are it's called proton exchange. Protons pop on and off all the time in hydrogen. Off in water. And so what would happen is, by having the pH, a water can take that hydrogen, and then a water can donate that hydrogen the next time. And so a lot of times in biochemistry, we just use it as a fudge factor. I should say, it's not really a fudge factor, but it could be the same hydrogen, but it doesn't have to be the exact same hydrogen because water is around us. Okay. Which you don't have that in vitro in an organic chemistry lab many times. In fact, a lot of times you deliberately try to exclude water so you can get higher yields. In our body, we don't have to do that. God has made us to where we have these enzymes that are these nice little factories, and so if there's a water in there, it's meant to be in there. Okay. All right, so we have this, but we still haven't gotten rid of our first product. Okay, so the way to do that, once again, they just assume that you know what's happening here, because you would have seen this in organic chemistry. So I'm going to actually draw this all the way out. The only thing happening, there's nothing happening down here. Please note, there's absolutely nothing happening right here. So I'm just going to call all of this R or something like that. Okay, let me get a different color. So maybe I shouldn't call it R because there's the first R up there. There's the R, the C, CO2 minus, that's just a carboxylate. Double bond N. That hydrogen's not all that important anymore. I'll just call it Y. Why? Because I love you. That kind of thing. All right, just because if I called it R, I don't want you to confuse it with the other R, the other generic R. Right? Because it's like that Y, which is all that pyridoxal ring, it's not important and stuff, but water is. And so what happens here, let me change colors. We have water coming in. They're showing it up here as it's coming in, but they don't tell you what it's doing. Water's a great nucleophile. We have to think what's delta plus or positively charged that water can attack. Okay, what do you think it can attack here? Let's either positively charged or delta plus. The nitrogen, and you know what? When you're first learning organic chemistry, that would be what would make the most sense. It's positively charged, right? Something that's delta minus. It's got a lot of electrons. This one has an electron deficit. But this is one time when it doesn't do that. It's one of the reasons why it doesn't do that. And the reason why is because which is more electronegative, nitrogen or carbons? Nitrogen is more electron. So what's the most electronegative atom on the periodic table? Fluorine. So the closer you get to fluorine, the more electronegative you are. That is something hopefully you learn in Gym Chem. If I had to say there's one important thing to learn in Gym Chem, it's electronegativity. It's like 90+% of chemistry relies on that. So nitrogen is a little bit more electronegative than carbon. So even though the nitrogen has a positive charge on it, that carbon is even more electron efficient. Okay, so what happens here is these come in, smack that carbon. Boom. Okay, sound effects optional. And what happens are these 2 electrons here are going to go to that nitrogen. Technically, it is reversible. This is all one, they're showing all as one step. I'm just trying to show it all out, just so that way you guys understand. Plus, those who are in biochemistry haven't covered this yet, you can always help me explain to others what's going on, hopefully later on. So now there's only one bond there. Oh, whoops, that's supposed to be a different color. Okay, the nitrogen has a hydrogen. And what we do all the time in biochemistry is that these 2 electrons could come and take one of the hydrogens off that water. Okay, so that's why I'm going to show it like that. But once again, since it's water, those hydrogens can pop on and off. Okay, nitrogen, CH2, R. There's still a positive charge on that nitrogen technically because it's got 4 bonds. Okay, and we've got OH. Okay, so that's the first step. And then the second step is really just a repeat. These 2, it doesn't have to be those 2, but 2 of the lone pair electrons from the oxygen go down, and I just do that because I'm right left-handed, and it's on the left-hand side. That's the only reason why I picked those 2. You don't have to pick those 2. Boom, it's gonna collapse to smack that carbon. Okay, to remake to make what's a ketone. Something has to break or give. We have a couple possibilities here. One of them is going to be really important later on because we'll get to it later. But it's going to be the 2 electrons between the carbon and the nitrogen can come back down. And once again, these 2 electrons coming down can swipe that hydrogen off because you're only swiping off the proton, you're not swiping off the electrons. Okay, and so the result is, I'm going to actually have to move some of this over. Oh, wow, that's really ugly. I didn't move the picture. Sorry. The result is, whoops, wrong color. We have the R, that carbon, the CO2 group. Okay. We have the nitrogen with its hydrogens. And it doesn't matter if you do it as 2 hydrogens or 3 hydrogens there, because once again, it depends on whether or not there's water around. CH2, Y. Oh, I called that R, I'm sorry. See, that's just habit from organic chemistry. But the oxygen that had been the water is right here as a double bond. They called this would be product number 1. See, there's a lot that goes into it. And it's called an alpha keto acid. These are very important in vivo, in biochemistry or biology. Why are they called alpha keto acids? And this would be the enzyme is still technically modified. We have to get our enzyme back. That's why we did all of this for the pink. We haven't honed it yet. My old boss would have hated me. He hated it when we made new verbs like that. All right, but yeah, this is the ping of the pong. All right, so why is it called an alpha keto acid? Does anyone know? What does the alpha mean? Pardon? It's on the first carbon. So, I don't know about gen chem. In organic chemistry, you learn how to number carbons. There are 2 different ways. There's the one where this would be carbon number 1 because it touches the most oxygens. Okay, and so this is carbon number 2, and if that was a carbon, it would be carbon 3, and so on and so forth. 1, 2, 3, 4, 5. Because there's a higher priority. But they like to make things more difficult, I guess. I don't know. They also like to use Greek lettering system. Okay, so what would be carbon number 1? I call it ground zero. That has absolutely no scientific meaning whatsoever. But that's the ground zero, the very first carbon. So the one next to it is called alpha. Okay, the one, if this was a carbon, we'd call beta, alpha, beta, gamma, delta, so on and so forth. They just use it, and so it's just another way of giving those are called locants, the ones and the numbers and the alphas and the betas. It's just another way of doing locants. And so that's why this is alpha, this is a keto group. So it's alpha keto to an acid. So that's a carboxylic acid. So that's where we get alpha keto acid. Just like that up there, even though it's not labeled as such, technically what we started off with was an alpha amino acid. All of your naturally occurring amino acids that are used to make proteins are alpha amino acids. I say that with a little asterisk to clarify the acid that was used to make proteins. There are amino acids in your body that are important that are not alpha amino acids. We have some that are beta amino acids. So therefore, the amino group would actually be on this carbon right here. That was a carbon. Okay. So there are times they're just not used to make a protein. They're used for other things, as other signals. Okay, so I'll go ahead and in class. Okay, so this is what it's showing. Ooh. Let me see, can I move this around? Oh, good. No, move that all down. So just to do the review, see we have the lysine from the enzyme with its imine or shift base. You got the attacking here to where now the imine has shifted to what it was the incoming amino acid. We get the quininoid, the intermediate collapsing, which is just a rearrangement reaction. And then we get the water coming in to pop that off. So then we got the first reaction, or I'm sorry, the first product. So this was all Ping-Pong would be going backwards, but with just a different amino group, or a different amino acid being formed. Okay. Then, since it's not being recorded, but we used to have this collaborator. And he would work on enzyme mechanisms and stuff too. And he would always say, you go after the lowest hanging fruit, which is kind of a common thing. So you go after whatever is the easiest thing to attack. But then he would also then say, you go after the child playing in the street, which kind of a little troubling. He's a little odd. Okay, but I'm sure the people, I won't say his name, but I'm sure the people who've worked with him know exactly what I'm talking about. To my knowledge, he's never taken a child. Dear God, please don't ever take a child. But that's beside the point. He's a father even. Of course, his kids are now grown because he would be getting up there in years. But yeah, so the lowest hanging fruit would be this hydrogen here. And this is one of these special things about those shift bases is they can help absorb the movement of electrons. Okay, so it takes just that hydrogen, just the nucleus. You know, it's a nucleophile. It just wants that nucleus. The electrons before that were holding it together, these electrons right here, will actually stay. But we can't leave them on that carbon, otherwise that carbon's negatively charged. And carbon, that's called the carbanion. You'll learn in organic chemistry that's not typically stable. And so they flow down towards that nitrogen. Boom. Sound effects optional. That nitrogen now would have too many electrons, as I mentioned before. So two of the electrons that had been holding it in that double bond, or that imine, that shift base, will now flow towards this, between these two carbons, boom, to make a new double bond. This double bond will swing down here to make a new double bond, and this double bond right here will swing right there, because nitrogens can have lone pair electrons. They can be either positively charged or have those lone pair electrons. So that's why pyridoxal phosphate, PLP, that's what the abbreviation for this entire ring is called PLP. It's really, really good for the movement of electrons. Because electrons can flow this way, and this reversible electrons can flow back. Okay, and so now I'm just going to redraw everything. This is just to show that it goes backwards and frontwards. Let me see if I can erase. No, it's been too long. Okay, so that's what I was afraid of. Let me see if I can. Good. Let's draw everything. I try to keep this color-coded correctly, but I apologize if I don't, if I mess something up. So now the double bonds between the two carbons, there's still that nitrogen. And once again, there are things hanging off of it, but that's not that important. There's a double bond there. There's always a double bond on that opposite side. It's called P for para, which means opposite. So just in case I say that. And one thing that I haven't drawn in here is there has been a hydrogen on these. It's just implied many times. So that's why that nitrogen is neutral. Okay. So that was everything that was in the yellow. Then we have that nitrogen that had been part of it's now double bonded to that carbon R carboxylate. Okay. Everybody want to get caught up. And if you had need for organic chemistry too, which I don't know that you guys did. All right. But one of my sayings was whenever we were doing attacking the carbons, and we would go from things that were carbon along street, like what's called centrifugal intermediate, we would simply make the intermediate and then we would break it. You make it and you break it, or you collapse it. And so we made this intermediate. They use the word quininoid. Did I say it right? For this specific intermediate here, that's not. It's just the term for this kind of ring. It is important. Like, how many people have heard of coenzyme Q? Like, maybe even in the health aisle. Like, oh, you take CoQ. CoQ can make a quininoid intermediate too. This word gets its Q. All right, and so it does electron transfers similarly. Okay, so now we're just going to reverse it. That's going to reform the double bond that was there before. Something has to break or give. And what it is this double bond is going to reform between what I will call the top carbon of the ring and the one on the right-hand side. And then what also happens is this double bond has to break. And what it does is it's going to come out. And just like we had over here a general base, we can have it something called a general acid, which means it's just going to donate a proton. It may vary a little bit from enzyme to enzyme. Like maybe there's already maybe it's something like this B, which is shown, which would be a BH. So maybe that B can give up that H again to reform the enzyme. So, or maybe it's water. Like I said, many times it's water. Or something like an aspartic acid. Or another amino acid that can do that. So I'm just going to have it as a generic H. Because it's just a general acid that was taken. Okay, so let's draw what this looks like. Just because I'm running out of room, I'm going to go down here. I always start with things that didn't change. There's still a nitrogen here at the quote-unquote bottom. And it's still a part of a ring. My ring's going to get squattier and squattier, I bet, as I go along. There's still 3 things hanging off. But now that double bond is here and that double bond is right there. There's only one bond up to that carbon that had a yellow hydrogen on it. I'm going to have to kind of draw it at an angle because I've run out of space. Now it's got that blue hydrogen. And it has everything from the original amino acid still. There's still a nitrogen. That nitrogen is still double bonded to a carbon. It still has a hydrogen here. So technically, I didn't put it in, but technically it would have been positively charged the way I have it drawn. There's an R. And the carboxylate. This is kind of squatty. Okay. Right, done. We still haven't successfully gotten rid of that nitrogen off of the originally red amino acid. Right? It's still attached to the enzyme's active site. So what is important here is typically it's a water, okay? It's going to come in. It's called it's like a hydrolysis reaction. of sorts. And this is what I drew out towards the end of the last class. So we have a water. And just because I don't have a lot of room, this is the part of the water that is the nucleophile. It's the lone pair electrons. Hydrogens by themselves cannot be a nucleophile except in one circumstance. Does anyone know when can a hydrogen be a nucleophile? If this is biochemistry at PhD, that's some credit. You don't see it very often in vivo. It's called a hydride anion. When hydrogen's got an extra electron, it's got 2 electrons, it's negatively charged. In vivo, it's not happy, so in vivo it doesn't typically happen. Usually when we do see it as a hydride, it's really attached to something like NAD or NADH, or it's attached to the cofactor. It's not just a free hydrogen out there floating around with an extra electron. Because it's not happy, it's very reactive. Okay, so this is going to come and it will attack that carbon. Oh, whoops, I forgot to change my colors, sorry. I've been trying to do all the electron pushing in, what is that, green? And this will, one of the bonds of the double bond will break. I'm not skipping any steps. Like almost always in biochemistry books, they assume that you had biochemistry, they assume that you had organic chemistry. So they would actually show this all at once to where this oxygen replaces the nitrogen here. And so it becomes a ketone. And it just shows it's one step. I'm showing it how the electrons actually move. Or how it's proposed that the electrons move. Okay, so once again we draw things. It didn't change. I am going to move stuff up, so that way it gives myself a little bit more room. Okay. So let's draw the nitrogen at the bottom of the ring. All the double bonds didn't change this last time. That's C with the hydrogen and a hydrogen. Nitrogen, hydrogen. Only one bond now to the carbon. There's the R group hanging off the carbon and the CO2 group, which is negatively charged. And I am going to skip the step of the hydrogen coming off. So now there's only one. It's an OH group instead of OH2. Because in vivo, it would be an OH2 positive. That oxygen is not going to stay to be positive. Okay. Then it's going to happen again. And so 2 of the electrons, it doesn't matter which of the 2 electrons of the oxygen is going to go. And what is positively charged, or delta plus, is that carbon. So that's why I say the most probably the most important thing in all of general chemistry to remember is the rules of electronegativity. Carbon is much less electronegative than oxygen. Oxygen is the second most electronegative atom. And so that's why the electrons, that carbon's considered delta plus, or just slightly positively charged. The oxygen's delta minus. So we get that boom, sound effects optional. Something would be breaking or giving, and what it is that bond between the carbon and that nitrogen will break, okay? And that nitrogen is going to take off the hydrogen. There's a lot of little arrows there, but that hydrogen can easily pop off because it's a proton. It's not going to be the electrons. Electrons stay behind. Okay. So, now if we draw what didn't change, like I said, and this has got to happen really, really fast in vivo, and it's reversible, because otherwise you would die. Technically, all of these would be positively charged, the way it's drawn. I'm trying to keep the color scheme correct. So now that nitrogen is attached to the enzyme or the enzyme's active site, and we have our first true product. There we go. Siri. The bane of my existence. Like, why did they put that there? That's just not good for left-handed people. Okay, and so there's an R. Looks like that. Alrighty. And so that's our first product in that ping-pong. The ping has happened. Okay, the nitrogen that had been originally part of that amino acid is now stuck in the enzyme's active site to await the pong part of the reaction. And so this is called an alpha keto acid. I've already explained that before, but just to review, it's called, there are two different ways of doing what's called locants or numbering systems. One is using numbers. This is the highest priority carbon. So this would be carbon 1 and 2 and 3. If that was a carbon, it would be 3 and so on and so forth. But another one is, I called it ground zero. That is not the scientific term for it. But then one carbon away is called alpha. And if this is a carbon, that's the beta position. And it goes alpha, beta, gamma, delta, based off the Greek lettering system. And so because of that, they called this an alpha keto, because that's a keto group, acid, because that's a carboxylate or carboxylic acid right here. Okay, so that's why this is called the alpha keto acid. Before it was an alpha amino acid, because that alpha carbon had an amino group on it. Those are the amino acids that are used to make proteins in your body. Okay, so that's our first product. But the second product would be the new alpha amino acid that you're going to get. Whatever was going to be the recipient from this amino group right here. Okay, which I'm going to undo that one. I should have used the arrow. The recipient of this one right here, which it does have lone pair electrons. So it can go and do attacking. Are there any questions so far? Like I said, I'm trying not to skip any of the steps. Just fall asleep on me. All right. I don't know about you, but having to do these really long passwords is a pain. Makes it easier to make mistakes typing things in. Okay. All right, so what's going to happen next? Let me move everything up. We got rid of that first product is now gone. It'll be released from the active site. It'll go on to do its own thing. So for example, in vivo, depending upon what you need in your body, if you need energy, perhaps what that is, that alpha keto acid is now acetate to go into the citric acid cycle. This is one example of a possibility there. Okay, so let me do a different color now. I'm running out of colors. I'll use this ugly one. So we have the next, it's actually another alpha keto acid that's going to come and accept that nitrogen, okay? And so here we come, it looks like this. There's the ketone. There's the carboxylate. And there's its R group, which, if you want to differentiate the fact that it's not the same amino acid as before, I'm going to put R prime. Use the letter 2.2. This is R is the generic X in organic chemistry. Does anyone know why? Why do we use X in chemistry? What does X mean? No, that's XE. It does mean something. And I don't know why they chose it. It means it's a halogen. Right. Yeah, generic fluorine, bromine ion. And so, yeah, that's why we don't use X. Just like typically they don't like to use Y, because Y is the generic one that's used for leading groups. I don't know what the chemists got their rules, but they like R. They just like R. So, instead of X. Whereas in algebra, you know everything's X. Okay. So this is a nucleophile. This nitrogen's got lone pair electrons that can go and do attacking. What do we have here? We don't have a lot here. That's going to be electron deficient, or delta plus, if you prefer thinking of it deltas. Like, it will not attack that oxygen, because those oxygens, they are going to be negatively charged. So what can it attack? What is delta plus? And if you need to, which is a good practice for those of you who are currently in organic chemistry or haven't had organic chemistry yet, you can put in the delta minuses and delta plus. So if we just start, those oxygens are already negatively charged. What about this? If we compare the ketones, oxygen and carbon, which one is more electron negative, the oxygen or the carbon? Oxygen. And so the way that they show that is they put a lowercase delta minus, and so therefore the carbon is delta, lowercase delta plus. Okay. that little squiggly thing is a lowercase Greek delta, whereas the triangle is the capital Greek delta. It actually does have this similarity to derivatives. That's the same thing that they like to use sometimes for derivatives and things, because derivatives is a small change. That means it's a small change in the electronegativity. So there is a rationale behind some things that they do use. Okay, so now what do we have? What do we have that nitrogen over here can go and attack? That's delta plus. I kind of narrowed it down for you. Boom! The carbon of the carbonyl. That's also called the carbonyl group, or an acyl group. Okay, and something that's the breaker give, and it's the double bond will come out, and it's going to take a hydrogen. Okay, I'm just going to show it. It can take it from a general acid, but it's going to make an alcohol right there, just like it was an alcohol before, right here. See, it was an alcohol. Essentially, it's a reversal of what we just seen. It's just that it's a different amino acid that's going to be forming. Okay. So now we can go through and draw everything that didn't change. Hopefully you're kind of getting a feel for this. We have the nitrogen down at the bottom of the ring. Double bond, double bond, double bond. 3 things hanging off. Ooh, I did not leave myself enough room. It's got this little tiny carbon. And if you don't mind, I'm just going to go ahead and do that hydrogen. Well, no, I guess I can still go ahead and color code it. To the nitrogen, hydrogen. This is really getting to be it's now attached to that carbon, which has the carboxylate, which has the R prime, which now has the alcohol. Okay. That's called a tetrahedral intermediate. What does tetrahedral mean? 4. There's 4 things. So this carbon right here, right there, is a tetrahedral intermediate. This is where every time, sometimes we even abbreviate STI, every time that you make that tetrahedral intermediate, you're going to break it. And so we made it, so now we're going to want to break it some way or somehow. Okay. Alrighty. So I'll give everybody a moment to get caught up. Okay. The way that we're going to break this one is a little different than what if what you may have seen in organic chemistry because of the presence of this being an imine or shift base. Which one is it? I'm looking for this one. Okay. So what's going to happen is that nitrogen is attacked at once. It's going to attack it a second time. Boom. And this will break off to form water. You get your water back that you had before. It's just, so here. Now let's just go ahead and draw, oops. So let's just draw it all out. I think my rings get bigger every time I draw this. 3 things hanging off. That carbon, hydrogen, hydrogen, nitrogen. But now the imine is between the nitrogen and the, what is that, pink? The pink carbon? CO2 minus, okay. And we have the water that's free. So we lost the water. I'm just going to draw it down here. It doesn't really matter where you draw it. But the oxygen that had been a part of the second substrate, that second alpha keto acid, is now the oxygen that's in the water. Oh, what's this? Was the H. I forgot the little bar. We put it in. Great. Okay. So now we want to get rid of that. We need to get rid of that nitrogen, right? And what we're going to do, does anyone know what's the one thing that we haven't gotten back by definition? In order for this enzyme reaction to work, what's the one thing that hasn't ever come back? The enzyme. Okay, we got to get the enzyme what it looked like in the beginning. And we haven't done that yet. Enzyme's still kind of sitting here, but it's not attached to this. And so all that's going to happen now is that the enzyme is going to come in and will replace the, what is that, red nitrogen? So that original enzyme's lysine will come in to do the attacking. Okay, so this was the enzyme with its lysine. I know I haven't drawn on the other side. That was freed from the very, very first step. And all it's going to do now, whoops, I forgot to change colors, is it's going to come in and smack here to free up the nitrogen. Okay, and so what will swing down as this comes down, then this will pick up the hydrogen, which will just be off of like a general acid, or it can be off of the lysine right there. And you get your final Pong reaction, or product, I should say, the Pong part. And so now we've got the pink carbon, it picked up a hydrogen. We've got its R group, its carboxylate, and it has the nitrogen from the original amino acid. Oops. And then we've got our enzyme back. So that nitrogen, all of this carbon double bonded to the nitrogen, which was part of the lysine, which is a part of the enzyme. So that would be the last step. Give you a moment to get caught up, because I didn't want to skip anything. Okay, because then I'm going to show you a much neater looking version, but it only shows it going in one direction because it assumes that you would have had organic chemistry to know how to do the reverse. Which is right. Briefly, I wanted to show, I said I haven't tried the update. Oh, that's not it. Browser. Let's see if it will come up. How fast it comes up. Oh, and by the way, if you've ever had blood tests done, you're like just your lip. Sometimes they call it lipid levels, but technically it's not your lipid. But just your blood panel done, and it has an AST and ALT. This is also ties in for biochemistry. That's your aminotransferase. And that, does anyone know? Well, actually, probably here. Yeah. The aminotransferases, those two in particular, are used to indicate like your overall general health, especially for your liver. If your liver starts to get taxed, then these aminotransferases, which are normally in your liver, gets upregulated. But yeah, those are aminotransferases. That's another. We use it as a biodiagnostic tool, but this is to show you how healthy or unhealthy you are. And there's a whole host of reasons why. Ooh, I think that's it. Let me just double check on this one real quick. This is called the active site. Okay. And so here we see, oh, it won't let me point out right there. But here we see the important lysine, which I also give you guys the cheat sheets for the amino acids and proteins. Lysine, this would be the nitrogen, that's the end of the lysine. That's attached to pyridoxal phosphate, which would be the business end of the aminotransferase. And we can see where there are other amino acids that help hold it in place. Okay. Does anyone know what do these lines indicate? Those are hydrogen bonding. Okay. And what are obviously hydrogen has to be involved. What are the other the recipients of hydrogen bonding? What are the other atoms that do hydrogen bonding? Nitrogen, oxygen, and no. Nope. Does anyone remember? In gym can you probably use it? And it, I was going to say, it's oxygen and nitrogen in vivo. Those are the ones that are the important ones. The other one's fluorine, and only does it with hydrofluoric acid, and which you never have in vivo. Do not take hydrofluoric acid, do not. But that's why oxygen and nitrogen are not really. Sulfurs aren't strong enough and polar enough to do it, and carbons definitely aren't. Only oxygen and nitrogen in vivo, and then technically hydrofluoric acid does. That's the reason why it behaves a little different than all the other like hydrofluoric acid, but in vivo, don't do that. You die. Okay, so don't do that. But this is just showing you how it holds everything in place. This is like the binding site for the pyridoxal phosphate and the incoming, amino group. Okay, but that's not what I was wanting to show you. I was hoping to have a really good. Is this one the one I was looking for? Let's see. Oh, unfortunately, they don't. It is, but, well, that's beside the point. Let me go back. But yeah, this is an aminotransferase. You know how it's very complicated structure, and we're just focusing in on this portion of it whenever we show the mechanism. They're just taking away all this extra stuff that helps hold the structure in place, or that may help hold the right orientation for the pyridoxal phosphate in place in order to some of the other. So this one, they didn't start all the way. I'm just going to walk you through it to show you to start to think about and be able to talk about these reaction mechanisms again. Remember, there are three types of reaction that aminotransferases do. One is the aminotransferase. One is the racemization reaction, and then the third one is the decarboxylation reaction. Okay, and so the racemization reaction is this one. You still form the exact same intermediate, but instead of what we saw before, so we saw the general base coming, taking that hydrogen, boom, the electrons come down here to reform a double bond. This double bond slips down here, and then you get the shuffling of the double bonds to look like this. Once again, that's called the quinoid. Then what happens here is you get that reverse, just like what we saw before. But instead of the hydrogen being added to this carbon, the hydrogen's added to what was the original C alpha of the amino acid. Okay, and so that's why the actual amino acid, the first amino acid, never leaves. So it's essentially the same reaction, but it never left. And then the enzyme comes back in with its nitrogen and kicks it all off. And so you went from either a D, it's not shown, a D amino acid to an L, or an L to a D. Here they're showing an L to a D. Okay, and that's really important because there's only one of these forms. I think glycine doesn't count because it's achiral, but all the other ones, in order to make it to what's normally used to make proteins, it has to be specific lineage or specific stereoisomer of it. Okay, so this is the enzyme that can do that. Secondly, another one, actually no, that's a different enzyme, so we won't do it. It's called racemase, which is actually really kind of cool because there's proline. Proline is one of the other amino acids, but proline, its R group is cyclical and it's stuck. And so the only way that we have to open it and to close it is with something that does react similar to this one. It's called racemase. Okay. So it has to be a little different. And then finally, this one does have a typo. This is the decarboxylation reaction. And once again, I want you to start to feel comfortable looking at these kind of arrows and this arrow pushing. So that's why you may want to look at this on your own, go over it again and again. Go online and look at some other examples because we're going to be talking about this at different times throughout the semester. But for the decarboxylation reaction, we still have the same type of intermediate here, but instead of the reaction occurring at this end, where we get the reversal and all this kind of stuff, we get what's considered a classic decarboxylation. The lone pair electrons here on this oxygen collapses to form what will be carbon dioxide. Something's got to break or give, and it's actually the bond between the two carbons that breaks. And so that's how you get CO2, which is a fully oxidized, fully used up. We used that carbon for all of the energy that it could possibly give us, and so it can leave the body. And then we get the electrons to sink down, then you go ahead and get the electrons to go back up, and then you get a very similar reaction to what we saw before, except we're not left with an alpha keto acid because we actually got rid of that extra carbon, and so you get an amine instead of an alpha keto acid or an alpha amino acid. You get an amine. It's called an amine because there's the carbon with the nitrogen directly attached to it. It's the single bonded nitrogen. If it was a double bonded, then it's called an imine. Okay. Are there any questions on this? Please practice. If this is new to you, you can come to me. You can work other examples out of electron pushing. It's really important whenever you start to do mechanisms. Okay, and like I said, this is Wednesday, right? So on Friday, we're going to segue from this and start going over basic structure terminology because the next assignment on your project has to do with structure of your enzymes. And we'll bring in the literature as well. So that way we can start to point out specific examples. Okay. Any questions?